In the previous lecture we were discussing about some aspects of the elimination methods, and where we ended up was the discussion on LU decomposition technique. To summarize what we discussed, in the LU decomposition technique we decomposed or factorized the coefficient matrix A as a product of a lower triangular matrix and an upper triangular matrix. The objective was to handle triangular matrices so that you can come up with an algorithm which is as efficient as the substitution method, the backward substitution method, or an equivalent forward substitution method which could be part of the Gaussian elimination method, but not the forward elimination part, which is of the order of n cube in terms of its computational cost. But where we landed up is that although the forward substitution or backward substitution, either of these are of the order of n square, but the LU factorization itself has a cost of the order of n cube. That makes the algorithm in terms of computational cost no better than the Gaussian elimination, but still in many cases we prefer to use the LU decomposition as compared to the Gaussian elimination. So what are those cases? So you have to remember that in Gaussian elimination there are two parts, one is forward elimination, another is backward substitution. Here there are basically two parts, one is the LU factorization, other is the implementation of the forward substitution and backward substitution. So if you see, let us consider a case where you have a system Ax equal to b, this type of system where A does not change but B varies. Classical example may be a situation where you have a particular layout of a spring mass system where you have different applied forces on which you try to solve the system, or maybe a structure, say you have a structure like this, some structure where the structure remains the same, only the load applied changes from one case to the other, and you are testing the structure with different loads. Or you have an electrical circuit where you change only the voltages, but the resistors making the circuit they remain the same. So if you just have an equivalent representation of say IR equal to V, where V changes but R remains the same, then what is the current that changes because of the change in V, say if you want to find out that. So with these examples we are seeing that there are possibilities where there is a simple algebraic equation, the right hand side of which may change under different circumstances, but the coefficient matrix does not change. So you have in general Kx equal to f of this form, where f is a forcing function, K is the stiffness matrix, so to say, just with an analogy of the finite element method. Your load vector f changes for studying different cases, but K does not change. So here K is equivalent to the coefficient matrix A. So when the coefficient matrix A does not change, then what is the advantage that you are having when you are having to simulate different problems where the coefficient matrix is the same, but the right hand side is different for different problems? Then what is the advantage? Advantage is that you have to factorize it only once, because factorization into L and U does not depend on the right hand side, it does not depend on B, it depends on only what is A. So if B varies in different cases but A remains the same, then you have to pay the price of LU factorization only once. Once you have done that, then for each and every individual problem you can use that same factorization without having to do it again and again, and then your cost is either forward substitution or backward substitution, which is of the order of n square. So you can use LU decomposition technique under certain circumstances where, or rather it is preferable to use LU decomposition technique for those circumstances where you have changing right hand side but the coefficient matrix does not change, so that every time you do not have to pay the price of calculating L and U. For calculation of L and U, that is for factorization, one can have a particular simple way of doing it which has number of calculations a bit less than what is required in this formula, in this formulation. This is known as Kraut's algorithm, so to say. What we discussed in the previous lecture about LU factorization, which is of the order of n cube. Now that number of calculations may be reduced to some extent if A is a special type of a matrix. So a special case when A is symmetric and positive definite. In that case you will have U as L transpose itself. This is known as Cholesky's LU factorization formula. But even then, although number of computations reduce, that you still have the computations for the factorization of the order of n cube. That does not change in terms of order, although exact number of calculations roughly become half of the original number of calculations, because here you had to calculate L and U, here you have to calculate either of L or of U, because one is the transpose of the other. So number of calculations becomes half, but that does not change the order, it does not change it from n cube to any other order. Now so but it is important to understand that that can be applied when A is symmetric and positive definite. So symmetric, what do you mean by a symmetric matrix A? When A and A transpose are the same, and positive definite, if you identify a vector V, any vector V such that V transpose AV greater than 0, then we call A as a positive definite matrix. So V transpose AV, where V is a vector, any vector. So if A satisfies these two conditions, then only you can use this Cholesky's factorization principle. So we have seen the Gaussian elimination, we have seen the Cholesky's or rather LU decomposition method with the Kraut's reduction or Kraut's factorization formula, and the Cholesky's factorization formula. Now before going ahead further, let us try to figure out whether the Gaussian elimination method will work for all cases or not. We have seen that if it works, how efficiently it works, that we have seen, that what is its computational complexity, whether there is any error involved or how the error is related to the implementation of the method, that we will come subsequently. But before doing that, we have to understand that will the method always work or not. So, let us consider an example. Say you are having to solve a system of two equations, solved by Gaussian elimination. Here epsilon is a small number, in the limit it tends to 0, but in the computer you can take it as a number which is very small as compared to the precision that is available. Okay. So, let us try to go through this problem. Let us say this is equation 1 and this is equation 2. So, the first step is the forward elimination. If you want to eliminate x1 from equation 2, then what would be the corresponding manipulation? Equation 2 minus equation 1 into 1 by epsilon, right. So, that will mean 1 minus 1 by epsilon x2 is equal to 2 minus 1 by epsilon. So, that is the consequence of forward elimination, and backward substitution x2 is 2 minus 1 by epsilon by 1 minus 1 by epsilon. So, what will be the value of x2? So, you have to keep in mind that epsilon is a very small number. So, 1 by epsilon is a very large number, minus 1 by epsilon is a very large negative number. In comparison to that, there is no difference between 2 and 1. So, it is minus a very large negative number, right, that means a very large negative number divided by a very large negative number. So, that is approximately 1. Then x1 will be 1 minus x2 by epsilon. So, that will be 0. You can see that clearly this solution does not satisfy the equations. So, if you substitute x1 equal to 0 and x2 equal to 1, it satisfies equation 1, but not the equation 2. So, these are not the correct solutions. To test whether we get something different by reordering the equations, let us reorder the equations. So, x1 plus x2 equal to 2, that is equation 1, and epsilon x1 plus x2 equal to 1, that is equation 2. Then let us go through the forward elimination step. Equation 2 minus epsilon into equation 1. So, backward substitution, x2 is 1 minus 2 epsilon by 1 minus epsilon. Epsilon is a small number, so this is approximately 1, and x2 is 2 minus epsilon, sorry 2 minus x1, sorry x1 is 2 minus x2, that is 1. So, this satisfies the given system of equations. So, the objective of this exercise is not just to see what is the solution of this very simple system, but to learn something out of it. So, what we saw here is that here the pivotal coefficient or the diagonal coefficient is small, and that created the problem. So, what is the origin of the problem? The origin of the problem is a small value of the pivotal coefficient or a small value of the diagonal entry. Here, because of exchanging the equations, now the order of the equations is changed. So, equation 1 becomes this one, its diagonal is 1, equation 2 it has its diagonal 1. So, none of the diagonals are very small numbers. So, what is the problem if the diagonal is a small number? So, we want the diagonal to be big enough in terms of magnitude. Later on we will see that this leads to a condition which is more formally known as a diagonally dominant system. That is, the diagonal element in terms of its magnitude dominates over other off diagonal elements. But before going formally into that, we can informally get a feel of that one. So, why do we require the dominance of the diagonal, or why do we require the diagonal to be large enough? You can see that essentially you are having to divide by the diagonal during the forward elimination process. So that if you remember, for example, in the Gaussian elimination you have a division by AKK. So, here that AKK k equal to 1 means A11, that is epsilon. So, that you can see even in this formula, where for manual implementation also we are using the same scheme. Now, if epsilon is a small number, then 1 by epsilon becomes a large number. So, division by a small number makes it so large that it can blow off and overweigh the effect of any other number. So, when it is 1 by epsilon, its effect has become now so large that it can overweigh the effect of the difference in the other coefficients. So, whether the other coefficients are 1, 2, 3, 5, 10, 20, 50, it does not make any difference, because 1 by the small number has become large enough to overweigh the effect of the differences in various coefficients. But if you are not able to resolve the differences in various coefficients, you are bound to get errors. So, you have to have a method where the differences in the values of various coefficients or the right hand sides, they need to be preserved. That difference should not be nullified. Now, by here, by the small number division, the difference between 2 and 1 has been nullified. So, as if it does not matter whether the right hand side is 1, 2, 5, 10, 50, 100, whatever, it is 1 by epsilon that dominates. So, you do not allow a small number to be there in the diagonal coefficient, because 1 by that will become a large number and that will overweigh the effect of any other coefficient. And That is why if such is the case, you will always have a chance that the Gaussian elimination will give you erroneous solutions, and the way out is to reorder the equations before implementing the Gaussian elimination, and that is known as pivotization. So, pivotization means you reorder the equations to reassign a pivotal row. Here the pivotal row was the first row. Now if you interchange those two, then the previous second row becomes the pivotal row. The pivotal row is considered to be such that the corresponding diagonal element is the maximum in magnitude of all the possible options that you have. So if you had for example 10 equations, out of that consider that row as the pivotal row for which the first diagonal coefficient is the maximum in terms of magnitude. Always remember that it is a magnitude that we are looking for, not maximum in terms of the signed number, it is the unsigned, the magnitude, because when you divide by a small number it is the magnitude of the number that will become important, not whether it is plus or minus. So pivotization essentially is reassigning the pivotal row in a way that you have the corresponding pivotal coefficient, which is the diagonal coefficient corresponding to that row, as the maximum possible in magnitude out of all the options of the equations that you have, and that will make sure that you are having the best possible option out of your given choice for implementing the Gaussian elimination. Even then it may be possible that that itself is not good enough, that even the best one has a very small diagonal coefficient, then such a system is prone to serious errors when implemented or solved by using the Gaussian elimination technique. That is one of the important things that we have to keep in mind. So Gaussian elimination will not always work, there are issues of diagonal dominance, and if those issues are satisfied, then only we expect that the Gaussian elimination will work well. Okay. Now so far we have seen algorithms where you have of the order of n cube or n square as the number of computations or the computational cost, but can we bring it down to of the order of n, and that is one of the very important and interesting questions that one would like to answer, because if that is possible, that can reduce the number of computations to a significant extent, and that is indeed possible not for all types of matrices, but for matrices which are tridiagonal in nature, and the corresponding algorithm is known as tridiagonal matrix algorithm or TDMA. It is also known as Thomas algorithm. Let us first try to understand that what is the motivation. In CFD this is a very important algorithm, and why it is so, because in CFD it is not very uncommon to get a tridiagonal matrix as a coefficient matrix. Why? Let us consider a one dimensional problem. Let us say that you have a grid point P, you have its neighboring grid points E and W. So you have AP phi P is equal to AE phi E plus AW phi W plus B. In general it is a summation of the coefficients from its neighboring grid points and of course the source term. You can write it in terms of indices. If you assign indices, you can write, if you call P as I, E as I plus 1 and W as I minus 1, you can write AI phi I is equal to Bi phi I plus 1 plus Ci phi I minus 1 plus Di of this form, where I is P, I plus 1 is E, I minus 1 is W. And this is logically obvious because in our discretization we make sure that events at a grid point are influenced only by its immediate neighbors, other neighbors do not come into the picture. If you use higher order interpolation techniques, then only other neighbors will come into the picture, but because of the linear profile assumption only the immediate neighbor will come into the picture. So you will have for a one dimensional problem only 2 neighbors plus the grid point itself makes 3 grid points involved at each time. So if you write it in a matrix form, so something into phi 1 is equal to something into phi 2, there is no phi 0. Let us say your grid point starts with 1, then 2, then 3, then 4, in this way up to n. So this is your domain. So phi 1 has phi 2, there is no phi 0, nothing called phi 0. So phi 1 and phi 2 are the 2 non-zero coefficients for the first equation, and there is something in the right hand side. For the second equation, something into phi 2 is equal to something into phi 3 plus something into phi 1 plus something. So the second equation involves non-zero coefficients as phi 1, phi 2 and phi 3. So phi 1, phi 2, phi 3 and something in the right hand side. Third equation will involve phi 2, phi 3, phi 4. So phi 2, phi 3, phi 4. In this way you will see that if you have considered all the equations, what are the non-zero terms which are involved? One is this diagonal term, this corresponding to phi 1, this corresponding to phi 2, this corresponding to phi 3, like that. Then the 2 immediate off diagonal terms and all others are 0. Such a matrix, such a coefficient matrix is called as a tridiagonal matrix, where you have the main diagonal and the 2 immediate off diagonals. So any algorithm corresponding to the solution of such a system is known as a tridiagonal matrix algorithm. So the first thing that we have understood is why the importance of tridiagonal matrix is there for a discretized system of equations in one dimensional problem. Next is how it is possible that you could come down to a computational complexity of the order of n. It is possible by considering that any matrix for its storage requirement, it requires 2 indices I and j. Here what we will do is, instead of using 2 indices I and j, we will just use one index for storing the entries corresponding to all these 3 diagonals together, and that is how we will have a linear storage system instead of having a 2 dimensional array for storing the system, and that is the basic origin behind improving the computational performance of this algorithm. So let us try to figure out that how we can do that. So, let us take a prototype equation of this particular form. AI phi I is equal to Bi phi I plus 1 plus Ci phi I minus 1 plus Di. Say this is the equation that you have obtained out of one dimensional discretization problem. Now, if you can start from the left hand side to the right hand side. So, your first equation will be A1 phi 1 is equal to B1 phi 2 plus D1, C1 will be 0 because there is no phi 0. So, you can write phi 1 is equal to B1 phi 2 plus D1 by A1, that means phi 1 is a function of linear function of phi 2. Second equation, A2 phi 2 is equal to B2 phi 3 plus C2 phi 1 plus D2. In place of phi 1 you can substitute as function of phi 2. So, this will give you phi 2 as a function of phi 3, linear function again. In this way you can use the previous step to write phi 3 as a function of phi 4, phi 4 as a function of phi 5. In this way phi n will be a function of phi n plus 1, but there is nothing called phi n plus 1. So, it is just a constant because there is nothing called n plus 1, n is the last grid point. So, now what we have to do is we have to systematize this approach. So, as if you know phi 1 you can know phi 2 from that, if you know phi 2 you can know phi 3 from that. It is not known explicitly, but implicitly if phi 1 was known then phi 2 would have been known, if phi 2 would have been known phi 3 would have been known. In this way if phi n would have been known then phi n plus 1 would have been known in this way, but there is nothing called phi n plus 1. So, that means in this way when you go to the last step phi n is known. So, what we will do, we will consider that you have intermediate steps of this form. Phi I as Pi phi I minus 1 plus Qi. This is the form that we look for. See phi 2 as a function of phi 3, sorry phi I plus 1. So, phi 2 as a function of phi 3, phi 3 as a function of phi 4 and linear function. So, linear function means of the form y equal to mx plus c, of that form. So, y is a linear function of x, phi I is a linear function of phi I plus 1. Okay. So, this is the form of the linear function where I depends linearly on I plus 1, where this Pi and Qi are not yet known to us. What is the immediate preceding step or immediate step before? Phi I minus 1 is equal to Pi minus 1 phi I plus Qi minus 1. That is replace I with I minus 1. Now, let us substitute this particular recurrence formula in the discretized equation. So, substitute in star. Say this is double star, substitute double star in star. So, ai phi I is equal to bi phi I plus 1 plus Ci in place of phi I minus 1 we will write P I minus 1 phi I plus Q I minus 1. So, from here we get A I minus C I P I minus 1 phi I is equal to B I phi I plus 1 plus D I. So, phi I is equal to B I by A I C I A I minus C I P I minus 1 into phi I plus 1 plus D I there is one Ci into Qi minus 1 plus Di, right. So, Di plus Ci Qi minus 1 by Ai minus Ci Pi minus 1. Now, you can see that this particular equation and the equation phi I is equal to Pi phi I plus 1 plus Qi, these are of the same form. So, let us call it triple star, let us give it 4 star. So, compare these triple star and 4 star. So, what you get? Pi is equal to Bi by Ai minus Ci Pi minus 1 and Qi is equal to Di plus Ci Qi minus 1 by Ai minus Ci Pi minus 1. Where you have to keep in mind that C1 is equal to 0 . Why? Because there is no phi 0 and Bn is equal to 0 because there is no phi n plus 1 and C1 equal to 0 implies P1 is B1 by A1 and Q1 is D1 by A1. And what is phi n? Phi n is P n phi n plus 1 plus Q n, there is no phi n plus 1. So, phi n is Q n. So, the first value of phi that you can solve for is Qn. So, you start with I equal to 1, then you go to I equal to 2, 3, 4, 5 like that. When you get I equal to n, you have obtained Pn and Qn and phi n is Qn. So, that is your forward elimination part. Let us systematize that. Before systematizing that, we can easily recognize that once you get phi n, then you can get phi n minus 1 because what is the formula that you are having? Phi I is equal to Pi phi I plus 1 plus Qi. So, if you know phi n, then you can calculate phi n minus 1. If you know phi n minus 1, you can calculate phi n minus 2. So, that is your backward substitution. In this way, the first value of phi you calculate is phi n, then phi n minus 1, then phi n minus 2, phi n minus 3. In this way, you end up with phi 1. So, that is how you solve for the unknowns from phi 1 to phi n. So, here also it is logically like divided into two parts, forward elimination, where forward elimination is this part, and the remaining is backward substitution, where it is a straightforward use of this formula. So, based on this, let us now summarize the TDMA. So, first is you input AI, BI, CI, DI, that comes from your discretized equation. Then you have P1 is equal to B1 by A1, Q1 is D1 by A1. Remember, the equation that you are looking for is AI phi I is equal to Bi phi I plus 1 plus Ci phi I minus 1 plus Di. Then for I equal to 2 to n, you can calculate Pi, this is a recurrence relationship. So, if you know P1, you can calculate P2 and Q2, if you know P1 and Q1, if you know P2 and Q2, you can calculate P3 and Q3 and so on. Then phi n is equal to Qn, then you have a for loop in which you put the formula for phi I is equal to Pi phi I plus 1 plus Qi. So, for I equal to n minus 1, it will start with phi n minus 1, phi n is already known, it will end up to 1 with I minus minus, that is you have an increment of minus 1, that is each I will be 1 less than the previous I. So, this is the forward elimination part. This is the backward substitution part, and you can see that the forward elimination part is having a complexity of the order of n, because there is only one for loop there which runs up to the order of n. So, the TDMA has an algorithm complexity of the order of n, not n square or n cube, that is a big advantage. Now, as for any other method, we would also like to know whether the TDMA will work for all cases or not, and to do that we will consider, or to assess that we will consider a very simple problem. So, let us say that we have a one dimensional system where you have the heat flux at the left wall as given say Q1, heat flux at the right boundary is also given same as Q1, the length of this one is L, thermal conductivity is given. We will assume easy numerical values so that we can evaluate that easily. So, the objective is to find out temperature distribution, steady state temperature distribution in the rod. The steps will be finite volume discretization and solution of equation by TDMA. Let us consider that we have 3 grid points. You can also consider to be it to be equivalent finite difference discretization also if you want, finite volume or finite difference whatever you want. Our focus here is not the discretization but the solution. Let us take the second grid point at halfway. So, this is L by 2 and this is L by 2. Let us form the discretization equation corresponding to the grid point 2. So, what is the governing equation? d dx of k dt dx equal to 0. If k is a constant, it is as good as d2t dx2 equal to 0. So, if you consider a finite difference discretization, it is T3 plus T1 minus 2 T2 by L by 2 square, that is equal to 0. Here delta x is L by 2. This is applied to grid point 2. That means T2 is T1 plus T3 by 2. For the boundary condition at 1, Q is equal to minus k dt dx at 1. So, k into T1 minus T2 by L by 2. So, T1 is equal to T2 plus QL by 2k. Okay. Let us consider this QL by 2k as a number A for simplicity. So, T1 is equal to T2 plus A. Then boundary condition at 3, in a very similar way T3 is equal to T2 minus A. It is physically obvious because heat is being transferred from higher temperature to lower temperature. So, T3 will be less than T2. So, now let us try to arrange these equations in this particular form AI phi I. So, A1 T1 is equal to B1 T2 plus D1. What is A1? A1 is 1, B1 is 1 and D1 is, in place of A let us give it a different name because A is already there, say alpha. So, this is equal to alpha, D1 is alpha. Then what is A2? A2 T2 is equal to B2 T3 plus C2 T1 plus D2. So, what is A2? A2 is, you can write 2 T2 and these as 1 and 1 in whatever way. So, this equation you can write as 2 T2 equal to T1 plus T3 also. So, A2 equal to 2, B2 equal to 1, C2 equal to 1, D2 equal to 0. Then for the third point, A3 T3 is equal to C3 T1 plus D3. What is A3? 1, C3, 1, D3 minus alpha. Okay. So, these are our 3 equations. C3 T, okay, that is T2, right. Okay. Now, you can go through the TDMA as it is there here. P1 is B1 by A1. So, P1 is B1 by A1, that is equal to 1, Q1 is D1 by A1, that is equal to alpha. Then P2 is B2 by A2 minus C2 P1. So, B2 is 1 by A2 2 minus C2 P1 1. Q2 is equal to D1 D2 plus C2 Q1 by A2 minus C2 P1. So, what is D2? D2 is 0, C2 is 1, Q1 is alpha. So, alpha by A2 2 minus C2 1 into P1 1. So, alpha. Then P3 B3 by A3 minus C3 P2. B3 is 0 divided by, let us see what it is there, A3 1 minus C3, C3 is 1 into P2 1. So, it is 0 by 0 form, indeterminate. So, you can see that the calculation of TDMA breaks down here. So, TDMA does not work for this case. Why it does not work for this case? If you consider the coefficient matrix, you will find what is the characteristic of the coefficient matrix here. Determinant of the coefficient matrix is 0, that you can easily verify. So, it is a singular coefficient matrix. So, remember that in whatever may be the method that we are using for solution, in Ax equal to b, x equal to A inverse b, inverse of a matrix is just like a sort of division. It is a systematic division considering a collection of numbers instead of a single number. So, if the inverse of A is what? Adjoint A by determinant A. So, if the determinant A is 0, if it is singular, then you can see A inverse has a problem. Physically, why the TDMA does not work here? I am giving this problem as an example because we have referred to this example earlier. You have this as actually an ill-posed boundary value problem, because you are having two flux boundary conditions where the fluxes are equal, and of course they should be equal because of one dimensional steady state heat conduction requirement, but that is already inbuilt with the governing equation. It is no new information. So, although you have specified fluxes at the two boundaries and they are equal, so it is physically consistent, but it is not giving you any additional information corresponding to the boundary condition. So, that gives rise to the singularity of a system. So, you can see an ill-posed boundary value problem, if nowhere detected otherwise, will face trouble when you are coming to solve the system of corresponding discretized algebraic equations. So, if the physics is somewhere erroneous in terms of describing the problem, somewhere mathematics will catch it. That is the beauty of mathematics, that if you are unable to represent the right physics through your mathematics, somewhere mathematics itself will interfere and detect itself that there is something wrong with the physics. So, TDMA may not work always. So, we will stop here today. In the next class what we will do is, till now we have looked into the implementation of different elimination methods. In the next class we will do an error analysis and we will try to figure out that what are the corresponding errors possible to be incurred and how we can quantify that in the elimination methods. Thank you.